Alright, the next section that we're going to do is section 8.6 on page 401. The MOSFET characteristics and parameters. What you have to note though is that much of the discussions concerned with the JFET characteristics and parameters applies equally to the MOSFET, as we will see just now. But then carrying on page 402, firstly the E-MOSFET transfer characteristic. Please note that the E-MOSFET uses only channel enhancement, you should know by now. Therefore, an N-channel device requires a positive gate-to-source voltage, and a P-channel device requires a negative gate-to-source voltage. Né? Then if we look at figure 844, it shows the general transfer characteristic curves for both types of E-MOSFETs. What you have to note though is there is no drain current when VGS is equal to 0. Né? As we've seen, which is opposite of the JFET actually. Therefore, the E-MOSFET does not have a significant IDSS parameter, as do the JFET and, as a matter of fact, the D-MOSFET as well. Notice also there is ideally no drain current when VGS reaches a certain non-zero value called the threshold voltage. VGS threshold, you can see here in figure 844 in both cases. Né? So, the equation for parabolic transfer characteristic curve of the E-MOSFET differs from the JFET and the D-MOSFET because the curve starts at VGS Thevenin rather than VGS off. Né? Make sure that you note that. Because it never intersects the vertical axis. So the equation for the E-MOSFET transfer characteristic curve is equation 8.4, where it says ID is equal to K times in brackets VGS minus VGS threshold squared. Né? The constant K depends on the particular MOSFET and can be determined from the datasheet by taking a specified value of ID called ID on at the given point of VGS and substituting the values into equation as illustrated in example 816. So let's just have a quick look at example 816 to make sure that we understand what is meant by this section. The datasheet for a 2N7002 E-MOSFET gives ID on is equal to 500 milliamps minimum at VGS is equal to 10 volts and VGS threshold is equal to 1 volt. Determine the drain current for VGS of 5 volts. Alright, the solution then on page 403. First I have to solve for K using the equation that we've just seen. So I can take out K by rearranging the formula. So K is equal to ID on divided by VGS minus VGS threshold squared, and that will give me an answer of 6.17 milliamps per square volt. So using the value of K, calculate ID for VGS minus 5 volts. So ID is then equal to K square in brackets VGS minus VGS threshold squared, and I get a value of 98.7 milliamps. So all that I have to do is just get the values from the data sheet and apply it into the formula. That's just for the E-MOSFET. Alright, next the D-MOSFET transfer characteristic. As we've seen, a D-MOSFET can operate with either positive or negative gate voltages. Né? So if we go and look at figure 845, I can see the general transfer characteristic curves for the D-MOSFET. The point on the curves where VGS equals to 0 corresponds to IDSS. Exactly the same as we had for the JFET. And the point where ID is equal to 0 corresponds to VGS off in both cases. So as with the JFET, VGS off is also equal to, in opposite polarity, V pinch off. Né? So the square law expression that we've seen in equation 8.1, where it says ID is equal to IDSS in brackets 1 minus VGS over VGS off squared, also applies for the D MOSFET as we've seen. Alright, so if we go and look at example 817, for a certain D MOSFET, IDSS is 10 milliamps, VGS off is minus 8 volts. Is this an N channel or a P channel? The device has a negative VGS off, therefore of course it is an N channel MOSFET. It also asks to calculate ID at the VGS of minus 3 and also to calculate ID at the VGS of plus 3. So just applying the formulas then I can see in the solution there. Firstly, for a VGS at minus 3, ID is equal to IDSS, in brackets 1 minus VGS over VGS off squared. I get an answer of 3.91 milliamps, and the same applies to value of VGS of plus 3, and in this case I get the value of 18.9 milliamps. Alright, then on page 404, a bit of theory that you have to know as well. The handling precautions. All MOS devices are subject to damage from electrostatic discharge, ESD. Underline that if you are ever asked this acronym. Because the gate of a MOSFET is insulated from the channel, the input resistance is extremely high, ideally infinite. The gate leakage current IGSS for a typical MOSFET is in the picoampere range, whereas the gate reverse current for a typical JFET is in the nanoampere range. The input capacitance results from the insulated gate structure. Excess static charge can be accumulated because the input capacitance combines with a very high input resistance and can result in damage to the device. So, to avoid damage from electrostatic discharge, certain precautions should be taken when handling MOSFETs. So there are 5 mentioned. Make sure that you do know them. First one, of course, carefully remove the MOSFET devices from their packaging. They are shipped in conductive foam or special foil conductive bags. Usually they are shipped with a wiring around the leads, which is removed just prior to installing the MOSFET in a circuit. Second one, all instruments and metal benches used in assembly or test should be connected to earth ground. The third one, the assembler's or the handler's wrist should be connected to a commercial grounding strap, which has a high value of series resistor for safety. The resistor prevents accidental contact with voltage from becoming lethal. The fourth one, never remove a MOS device or any other device for that matter from the circuit while the power is on. And the last one, do not apply signals to a MOS device while the DC power supply is off. Alright, that concludes section 8.6, which is concerned with the MOSFET characteristics and parameters.